Acidity by induction. You might see certain sets of molecules that you don't really have much knowledge of anything, or perhaps you have sets of molecules that look pretty much the same in terms of functional groups present. And this is an example of that situation. We have technically alcohol, 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 alcohol. They're all alcohols. So you expect, roughly speaking, a pK of 16 for each one of these substances. But the deal is this: they are all alcohols, but nevertheless, they do contain different types of halogens. The molecule here on the left has fluorine very close to that OH bond, and then chlorine on the second carbon from that position. The molecule here right next to it has only fluorines, so two fluorines. This one has two chlorines, and this one has fluorine and chlorine, but the chlorine now is the atom that is closest to the OH bond. And so here what ends up happening is what we call induction. Technically speaking, we look at the idea of dipole moments arising from having these electronegative atoms, bound to carbon. And the halogens are all more electronegative than carbon. Iodine, perhaps is the one exception, but bromine, fluorine, and chlorine, they're all more electronegative than carbon. So you expect to have a dipole moment going towards the halogens arising from the carbon. And the idea is that that dipole moment is going to pull electrons away. So think of this arrow, which is the dipole moment. Think of it as electrons running away from this carbon. And between fluorine and chlorine, fluorine is more adept at removing electrons from carbon. So you're going to have a higher dipole moment on the CF bond than you will on the CCl bond. Okay, so this is the way you use this information ultimately. Where you have more fluorines, you expect to have the most inductive effect via these dipole moments present. And removing electrons from this carbon ultimately means that that's going to be felt at this hydrogen, because if this carbon starts developing a partial positive charge, the electrons on the oxygen are going to be attracted to that carbon. In doing so, are going to somewhat deplete the electron density on oxygen, which itself will create its own delta plus on oxygen. And then this hydrogen will have its electrons moving towards the oxygen more so than it would have had if this was a regular alcohol with no halogens on it. So the two fluorines being present means that probably this is going to be the structure where the electrons are removed the most away from the hydrogen, and as such will make this more like an H+, meaning that this will be the most acidic substance. Right, so all of this induction effect of like pulling the electrons, almost like if you had a rope and multiple people were holding the rope. If the rope starts being pulled towards the left, everybody moves towards the left, right? But the extent happens greatest for the fluorine combo than the chlorine. So we would expect in a situation that having two fluorines versus two chlorines, the two fluorines will be the most effective at removing electrons and turning this substance acidic. The two chlorines will be the least effective, making this substance not as acidic as the counterpart. And in the case where we have fluorine and chlorine combos, well, here we have to be a little bit more careful about how we go predicting this thing. So the least acidic is the two chlorines, the most acidic is the two fluorines. I think you guys can see that relatively easily. But when it comes down to this mix match, you have a fluorine and a chlorine, but they just happen to be in different carbons. The idea is that the closer you are to this OH bond, the bond that's actually acidic, the more inductive effect force you're going to enact on it. So what you basically want to look for is the most electronegative halogen being closest to the OH bond. And for whichever the case that happens to be, you will end up with the most acidic counterpart between the two. So the molecule here has in fact that fluorine right next to the OH bond, whereas this one has the chlorine. Fluorine is more effective at withdrawing electron density than chlorine. Therefore, this molecule is going to be more acidic than that one. And here you can now have your entire trend 2 fluorines is the most acidic alcohol. Fluorine chlorine, where the fluorine is closest to the OH bond, is the next most acidic. Fluorine chlorine, where the chlorine is closest to the OH bond, is the third most acidic, and the 2 chlorines is the least acidic out of the group. So this is all via induction. We haven't really invoked anything else aside from these dipole moments, but hopefully you can see what's going on right here. It might actually help, especially at the beginning, to draw those dipole moments to kind of get an idea of what's happening. Then again, there could be other situations where there could be induction present, or maybe there is no induction, and yet one molecule ends up being more acidic than another. And the effect that may be able to explain it is resonance. We did talk about this example back in the first lecture, but technically speaking, aniline, which is this aromatic amine, if you compare it to the nitroaniline counterpart, which has this NO2 fragment on the opposite end of the hexagonal ring, what ends up happening is that that NH bond is more acidic in the nitro group containing molecule than your regular aniline, the one that lacks the NO2 group. And the way we explained that was based on the resonance structures that we can draw for this molecule, because it will have a lone pair on the nitrogen, which is next to that carbon-carbon's double bond. We can start drawing resonance structures, and that's what we did on the first lecture. We draw the first resonance structure, create that double bond, kick out the double bond that used to be there, form a new carbanion. And that carbanion, which, by the way, this is hilarious, kind of looks like a, not necessarily a sad face, but a very indifferent face right here, right? That's technically an electron pair with a negative charge, you know. If we now move that electron pair onto the next multiple bond, we create a new double bond, a new carbanion, and in the case where you do have the nitro group present, you have the additional resonance structure between this carbon and the nitrogen, right? And you create this final resonance structure. This final resonance structure is not one you can create with regular aniline, because it does require the presence of this NO2 group for this structure to even be present at all. So the fact that you have more resonance structures where you have that positive charge on the nitrogen present tell you that this molecule is going to be more acidic than regular aniline that has less resonance structures with a positive charge on the nitrogen. And this is a feature that you can use constantly in organic molecules. Wherever you see multiple bonds and lone pairs, there's a good chance that you could draw a resonance structure. That's not to say that the resonance structure might not explain what you're trying to explain, but it's a safe bet to give it a shot and see if it, remotely addresses the question at hand. Now, the last one is hybridization. And I did touch upon this in the second lecture in terms of the bond lengths and the bond angles of the molecules. But the idea still is that if you have a greater S content in your hybrid orbital, you get to see more of the nuclear charge because of that non-zero penetration to the nucleus. And the more S content you have, the more positive charge you see. Now, the more positive charge you see, if you think of this in terms of induction, the more positive charge you see on that carbon, the more the electrons of that CH bond are going to go towards the carbon. And in doing so, this H will become more like an H+, therefore turning this into a more acidic substance. But this only happens as you increase the S content. sp3 happens to be the substance that has the least amount of S content, only 25%, because it's 1 out of 4 orbitals. sp2 is 33%, sp is 50%. And what you end up seeing is exactly an increase in the acidity going from left to right, because we know the pKa of the alkane is about 50, that of the alkane is 44, and that of the alkyne is 25, and decreasing values of pKa imply greater acidity. And so here you can see, just by looking at the hybridization of the carbon to which the hydrogen is bound, the more S content that carbon has, the more acidic the CH bond is going to be. And that's not exclusive to just your regular alkanes, alkenes, and alkynes. You can apply that to other functional groups like alcohols. If you notice, we did talk about regular alcohols having a pK of 16, but then phenol, which is an alcohol, mind you, aromatic, but an alcohol nonetheless, has a lower pK of 9. And the reason for that is because the carbon to which that oxygen is bound is sp3 in your regular alcohol. But the carbon here on the phenol is actually sp2. So the S content of that carbon is greater, therefore the pK ends up being lower. Your substance is more acidic. And here goes yet another example. We have an amine, another amine, a third version of that amine, and then we have a slightly different version, but in fact this is an amide, no longer an amine. But let's take a look at the amines first. This is got a regular sp3 carbon bound to the nitrogen, whereas this nitrogen has a benzene bound to it. So that pH, get used to thinking of C6H5, which is your benzene hexagon bound to, in this case, nitrogen. So this carbon here is an sp2 carbon, part of the benzene ring. Same thing here, sp2 carbon. But here we have two of those benzene rings or phenol rings present and bound to the nitrogen. So what ends up happening is going from sp3 to sp2, you see a decrease in the pK from 38 to 30.6. Adding a second phenol ring onto the nitrogen adds an extra sp2 carbon that's withdrawing electron density. So you see another drop in the pK of the substance. And for a carbonyl compound that's technically an sp2 carbon, but that has, in addition to that sp2 hybridization, a really high polar bond, which by induction also removes electron density from that nitrogen, gives you an even lower amount. But the thing to kind of pay attention to is the fact that yes, you do have that induction effect, but it's not as dramatic as the change that happens from adding those extra sp2s into the picture, or even changing sp3 hybridization to sp2, right? You do see a decrease due to induction, but it's not as drastic, and hopefully this example makes that very clear. Okay, so with that all being said, we've basically talked about all of the main things in regards to acid-base theory. And if you do have questions, I encourage you to reach out and ask questions, and I'll try to help you out as best as I can. Other than that, I'll see you in the next lecture series. Bye bye.